Okay, so question 1 says the spreading of the wave as it passes around an obstacle is called spreading, means changing of shape. It's called diffraction. Okay, the bending of wave or the spreading of wave. Unpolarized light with a power of 8 watts is incident on a polarizing filter. What is the power of the light after passing through the filter? Okay, now you have a filter, right? Polarizing filter. Its job
Right.
is, and this is light. Light is a transverse wave. It is an
B.
electromagnetic wave. Yep, that's P. It's an electromagnetic wave, so polarizing filter. It is made up of two vibrations, vertical and horizontal,
Yep.
right? So the polarizing filter will absorb one of these two vibrations and allow the other one. So half of the
So it gets
intensity
stuck.
would be reduced. Yeah. Then 3 says the current I through a wire is I is equals to NAQV. Okay, NAQV basically. Which of the following is the correct statement for N? What does N represent?
Number of
Charge carriers per unit volume. Okay, so it is dependent upon the material of the substance of the wire actually. Okay, it is a property of a wire, because this is an
wait, why not B?
equal to the number of charge carriers. It's not the number of charge carriers, it's the number of charge carriers per unit volume. I've been
Oh, okay.
repeating this again and again. Okay, and it is dependent upon the material of that wire. Then 4 says, now again
What was the
diffraction.
full formula for that?
This one is right over here. I is equals to NAQV.
Okay, right, right.
NAQV. All right. Now
Okay.
the 4 diagrams represent moving wave fronts that are one wavelength apart. Okay, their difference is lambda. Now in each setup, diffraction will occur as the wave front passes through the gap. Which setup will produce the greatest diffraction? All right, they are one wavelength apart, and let's see which of these will produce the greatest diffraction. Okay, if you look at the part B, the wavelength is small, and the slit size is also small. If you look at A, the wavelength is relatively larger and the slit size is relatively larger. If you look at option C, the wavelength is large and the slit size is also compared to that. Okay, if you look at the slit sizes, they're not constant, they're changing, meaning the slit sizes are changing relative to the wavelengths. So if you look at these two, option A and option B, they have the same wavelength and the slit sizes are different. If you look at option B and option D, the wavelengths are smaller. For diffraction to occur, this wavelength has to be as large as possible, okay, for maximum diffraction. And the slit
Okay.
size has to be as small as possible, okay? If the slit size is gonna be smaller than the wavelength, then more diffraction would occur. But if the slit size is larger than the wavelength, then no, possibly negligible diffraction would occur. So over here, the wavelengths are smaller, right? The wavelength, these two are wavelengths are smaller, so cannot be these because their diffraction is gonna be less than these two. Now, in these two, if you look at the slit sizes, option C has a smaller slit size compared to option A, right? So therefore, option C
Wait,
is
sir, can you
correct.
speak Hugin's principle?
Sorry? An electrical motor is being used to lift a load. The total input energy to the electrical motor is E, and this is a total input that is given to the electrical motor. Some of this energy is transferred in the useful gravitational potential energy. This is the useful energy, and the remainder is wasted. What is the efficiency? Okay, efficiency is the useful divided by the total. So useful is the gravitational divided by the total, which is input.
Input.
So
First
this is
one? Oh, no,
this
no, it's not the
it's
first
not
one.
this one. All right, so we can also express this
C, C.
e input as
No, B, B, B,
gravitation plus this. Okay, it's
B.
gravitation plus wasted, and gravitation is the useful. So yeah, it's B. Clear? Okay, question 6. A wire has a resistance of 8 ohms. The second wire has twice the cross-sectional area, twice the length, and twice the resistivity. What is the resistance of the second wire? All right, you've got one wire whose resistance is, let's assume it's 8 ohms. Okay, they told us it's 8 ohms. All right, it's 8 ohms. Now resistance is equals to rho L upon A. Now they told us that, and if you write it in terms of diameter, Okay, you don't need to write it in terms of diameter because they've given you in terms of cross-sectional area. Now they told us that there is a second wire whose cross-sectional area is twice the original cross-sectional area. Okay, resistance is inversely related to area. So if area becomes twice, the resistance is gonna become half. Okay, with the area effect. And then they told us that the length is twice and resistance is proportional to the length. So if resistance becomes length becomes double, then resistance is also gonna become double. And if resistivity becomes double, resistivity and resistance are also proportional, then resistance again will become double. So the 2 and the 2 will cancel out, and this R has a value of 8 ohms. So 8 2s are 16 ohms is your answer. Clear? Is this clear?
Yeah.
Question 7, the energy of a photon is equal to each of the SI base unit of H can be given as, okay, what is the SI base unit of
B?
H? H is equals to E upon F. Okay, you're
Is
saying
it
B.
B?
Let's see. E is the energy. Energy is kg ms minus 2 multiplied by m, which is m squared, divided by frequency is S inverse. S inverse will go up and it's going to become kg m squared s minus 1. It's E. It's not B. It's m squared,
Oh.
not m. Yeah. Okay. Then after 7 comes 8. Oscilloscope screen shows the transmitted
Wait, how is it kgm square?
because that's the unit of energy. Energy is force into displacement. The unit of force is kgms minus 2 and displacement is meters. So it's going to become kgm squared s minus 2.
Oh, okay.
Okay, now coming to this.
Whenever there's energy, will we always replace it with like F into like force into distance?
Yes, yes, yes.
Because
Correct.
there's so many formulas for energy.
Yeah, you are all. This is the simplest one. Well, all of them will give you the same units, but this is the simplest, the fastest one. Okay.
Okay.
Yeah, you can use any formula, it will give you the same units, but this is the easier and the fast one.
Like we can even use half mv square.
Yes, you can use that.
Oh, okay. Also like mgh, etc.
This is easier. Yeah, this is also easy. Half has no units. The m is kg and the meters per second is squared. So it's gonna become kg m squared s minus 1, minus 2 actually.
Uh-huh.
Okay. Yeah, and mgh and everything. But mgh is gonna become a bit more
So what are
complicated.
all of the formulas for energy? mgh, half mv square, f into s, and
If you are talking about electrical energy, it's power into time. If you're talking about strain energy, it's half kx squared. If
half
you're
kx
talking
square,
about
right?
or half fx. Okay, and there are many more, many more. So, well, these are the more relevant ones right now. We can talk about that later. Let's complete the paper first.
Okay.
Okay, yeah. So you have the oscilloscope screen over here. This is a transmitted pulse, and then this is a detected pulse. Pulse echo techniques can use ultrasound. When the ultrasound pulse reaches the boundary between two material, part of it is reflected and then detected. Okay, so you throw in the ultrasound wave. As soon as it reaches a boundary, some of it gets reflected and the rest of it gets transmitted. Okay, this reflected wave gets detected by a detector. This is the reflected and that's the transmitted wave. Now they're telling us that the speed of the ultrasound in the first material is V. Each division on the oscilloscope represents 10 microseconds. What is the approximate thickness of the first material? Okay, this is your transmitted pulse and this is your detected pulse. Detected pulse and the transmitted pulse. What's the distance in between them? The distance in between them will give you the time interval in between them. Okay, meaning it will give you the time it took for this reflected pulse to return back to the detector.
Okay.
Yep. So just a quick recap. The pulse is created or generated or transmitted from here. The stopwatch starts and you get this pulse on the oscilloscope screen. This pulse goes forward. It hits the boundary. Some of it is transmitted here as well. That's why the peak is lower than the actual peak because some of it got transmitted over there, but most of it got reflected back. And then this reflected back wave is detected at the detector. Okay. The time interval in between them can be calculated using these boxes by counting the boxes and multiplying them by the 10. So it's going to be 40 right? 4 into 10 is 40 microseconds. And you got the time for this wave to go forward, hit the boundary, and then return back. So the distance that it covered is twice the thickness. If the thickness is x, total distance covered in that time period is 2x, which is equals to, s is equals to vt can be applied. V is given to you, it's v, the speed is v, and the time taken is 40 raised to the power minus 6. And so x turns out to be v into 20 raised to the power minus 6, option A. Clear?
Yep.
9. Now, okay, an ultrasound pulse echo technique is used to produce an image by reflection from many boundaries. If the transmitted pulse is too long, the image produced is of poor quality. This could be because of energy of the pulse is too high, frequency of the ultrasound is too high, time in between the consecutive transmitted pulses is too short, or the wavelength of the ultrasound is too long. Okay, why will the quality become poor? Quality means quality is actually dependent upon the wavelength or the resolution. Okay, quality depends upon the resolution. And I think this is a repeat question, if you remember. All right. Now, the resistance of a thermistor decreases as the temperature increases. We know that from theory. Okay, as the temperature rises, the resistance of a thermistor will fall. It is used in a circuit to switch on a heater as the temperature falls. The heater will switch on when the potential difference across it is greater than a certain value. Okay, so if the potential difference across the heater becomes greater than a particular threshold, then it would switch on. Which of the following circuits would do this? Okay, so now if you look at option A, they told us that the heater will switch on after the as the temperature falls. Okay, now if the temperature is falling, that means the resistance of this one, this thermistor will rise, and as the resistance of this thermistor rises, that automatically means that the potential difference across the thermistor will also rise, because in series voltage is going to remain proportional to the resistance given that the current is constant, right?
Yep.
In series, the current is constant, so resistance and voltage are proportional. Therefore, as the resistance rises, the voltage rises. Okay, so if the voltage rises across this thermistor, then that actually means the voltage across the heater will also start rising. And as soon
Right.
as this voltage reaches a certain value, it will turn on. So option A should be the best answer. It's correct. Okay, if you look at option B, in option B, as the temperature rises, the resistance will rise and then this voltage will rise, but that voltage will fall. And as this voltage falls, the heater will not turn on. If you look at option C again, this is not correct and these are out of the way. Okay, the heater has to be in parallel to the thermistor. Option A. Okay, clear? Is this clear? A right angled glass prism may be used in an optical device to deflect a ray of light through an angle of 90 degrees. The light enters the prism along a normal and it is totally internally reflected. Okay, total internal reflection is occurring. State the necessary conditions for the light to be totally internally reflected at the boundary between the two materials. So conditions of total internal reflection. The first one is,
Angle of
yes, angle of
be
incidence must be
larger.
greater than 90 degrees. Sorry, not 90 degrees. It must be larger than the critical angle. Okay. The angle of refraction is going to be greater than 90. Reflection, total internal reflection would occur actually. But this is actually not the number one condition. This is the second condition. This is the second condition. The first one is that the light must be traveling from a denser to a lighter medium. And if you look at this ray over here, we are moving from lighter to denser. Over here, no reflection is occurring. But in here, you are moving from denser to lighter back. So now the condition is fulfilled. Moving from denser to lighter, then since the angle of incidence is going to become greater than the critical angle, so it is going to become totally internally reflected. Okay?
So angle of incidence should be greater than critical angle, and
And the ray should be
it should be
moving
passing.
from denser to the lighter medium. From
Okay.
denser to the lighter medium, okay? The glass is denser than air, so
Can
denser
you
to
see how
lighter.
the marking worded it?
For light traveling from high refractive index to a lower refractive index, meaning more dense to less dense, okay, denser to lighter. And then angle of incidence is greater than the critical angle.
Okay.
Part B says we've got a drop of water forms on the outside of the prism. Okay, now this is water. Water has a greater density as compared to air. Now determine whether all the light will still be diffracted through 90 degrees by the prism or not. All right, so we need to see whether total internal reflection will still occur or not. Okay, so if this is your normal, then that means if this angle is 45, this angle is also going to be 45. If this angle is 45, then that means the angle of incidence is also 45 because this is a 90 degrees right angle triangle over here. Is this part clear?
Yeah.
Okay, angle of incidence is 45 degrees. What we need to find out is the critical angle of this situation. When you've got water and you've got glass, what's the critical angle? If that critical angle becomes more than this angle of incidence, then that means no internal reflection would occur. It would pass, it would refract. But this incidence angle, if it becomes greater than the critical angle, then yes, total internal reflection would happen. So now let's see. To find out the critical angle, if you remember, there was a formula. But before we find out, we use that formula, we'll need to find out the refractive index. Okay.
Sin I over sin R.
Yes, sine I over sine R. But over here, you've got the speeds. How are you going to use the I and R?
C over V.
Yeah, C over V. But what is C? What is V?
C is speed of
Is the
light.
speed of light. Right, so let's continue with this question. Okay, so they told us that there is a drop of water. So this is water over here. This is glass over here. Determine whether all the light will still be diffracted by 90 degrees by the prism. All right, so I told you that we need to determine the critical angle first. And the idea for the total internal reflection to occur is that the angle of incidence must become greater than the critical angle. Angle of incidence is 45 degrees. So let's find out the critical angle first. To find out the critical angle, we'll need to find out the ratio of refractive indexes. Or we'll need to, refractive index of okay, over here, what we need to put is we need to put the larger speed divided by the smaller speed. Okay, well, generally the formula for refractive index is C upon V. Okay, speed of light in vacuum upon speed of light in medium, but over here we don't have vacuum, right? So vacuum means less dense medium, right? Vacuum means less dense, and medium means more dense. So you have to put the less dense mediums. Less dense is water as compared to glass, right? So you have to put the water speed in the numerator divided by 2 raised to the power of 8. And this gives you 2.25 raised to the power of 8 divided by 2 raised to the power of 8, which is 1.125. You've got this ratio of the two speeds to get the refractive index. Now, once you have this refractive index, you can use it to calculate the critical angle. Now, see, whenever you are moving from glass to water, that means you're moving from denser to less dense medium, right? And from when you're
Yeah.
moving from denser to less dense medium, then the formula for this refractive index is gonna be sine R upon sine I, not sine I upon sine R. Okay. When you are moving from denser to less dense, this is the formula. If it was the other way around, if it was less dense to denser, then in that case the formula would have been sine I upon sine R. Clear?
Okay.
This
Yeah.
is this is
Clear.
a distinction. Now, so just plug in this value over here, 1.125 is equals to, what should the value for sine R be? The refracted angle for the
And then
critical
how to
angle.
know which one should we put first? Like which one should we put for the denominator and numerator?
In which formula?
For
This one or
the
this one?
first one.
This one or this one?
No, the first this one. Yeah.
The greater speed is going to come on the numerator and the lesser speed would come in the denominator. Get it?
Always.
Yeah. because see,
Okay.
it's vacuum upon medium. In vacuum, you have the maximum speed. In medium, the speed is going to become lesser than the vacuum.
Okay.
Okay. So now the refracted angle for a critical angle is going to be 90 degrees divided by sine of the critical angle. Remember,
Yeah.
we are finding out the critical angle. Critical angle is the angle of incidence. So for that, the refracted angle is going to be 90. Now find out the value for the critical angle. So it's going to be sine of C is equal to sine of 90 is 1 upon 1.125. And then find out the value for C, which is sine inverse of 1 upon 125. 1.125.
62.7.
Okay, so 63 degrees approximately. This means the critical angle is 63. What's our angle of incidence? Angle of incidence is 45. So is it more or less than the critical angle?
It's lesser.
Yeah, okay, it's lesser. So will total internal reflection occur?
No.
No, no total internal reflection occurs. It has to be more than
Also, how did we get that formula? Like n is equals to sine over sine c.
this one.
Yeah.
The refracted angle for the critical angle is always 90 degrees from that idea. Critical angle is the angle of
Okay.
incidence, and the refracted angle for that critical angle is 90. And you know this from theory, right?
Also, isn't it n is equal to sine I over sine r?
N is equal to sine I over sine R in this case, when you're moving from less dense to denser medium.
Oh, okay, right.
But over here, we are moving from glass to water.
Denser to less dense.
Yeah, so this is going to be reciprocal. All right.
Okay.
Is this clear? Do you want to take a picture of it?
Yeah. Okay.
Now, question 12 says the speed v of water waves is in shallow water is dependent on the depth of the water, as given over here. V is equal to square root of g into d. All right, d is the depth and g is the gravitational field strength. Explain how the transverse waves move across water. Okay, you're talking about transverse waves. Transverse waves move are those waves in which the direction of vibration is perpendicular to the direction of oscillations. That's how they're gonna move. So in transverse waves, direction of vibrations is perpendicular to the direction of propagation of wave. Check out the marking scheme for this because it's theoretical. Oscillation of water molecules and oscillations are perpendicular to the direction of propagation of the waves. So we got the marks. Okay, we did mention the vibrations, we did mention the perpendicular direction. Then part B says student investigates the speed of water waves using a tray of water. He quickly raises and lowers one end of the tray. So if the tray is lowered and raised, that means it would be producing water waves. A wave moves across the water and is reflected, then it reaches the other end of the tray. The student measures the time taken for the wave to travel 4 lengths of the tray. Okay. He also measures the length of the tray. If the length of the tray is L, then the distance that the water wave has traveled is 4 times of L. And for this distance, the time has been measured. Let's assume the time has been measured to be T. And the depth of the water in the tray has also been measured. He repeats this for different depths of water. Describe how the student can use his results to verify this experiment by a graphical method. All right, so a unit 3 type of question. According to this formula, V is equal to square root of G multiplied by D, where G is a constant. So I can say that V is proportional to square root of the depth, right? And if V is
Okay.
proportional to the square root of the depth, then the graph that I would draw, it should be expected to pass through the origin, and it should be a straight line because this is a typical direct relationship graph.
How would we know which one goes to the like axis?
This is the dependent variable, and this is the independent variable. The y value is the dependent and the x-axis value is the
Okay.
independent value. Okay, so now these you've decided the graph. the sketch of the graph. Now, all you need to do is just describe how this experiment is going to be performed to verify this result. So we need different depths. So use different depths, different depths of water. Then he takes a time for 4 lengths of water, but the speed is distance upon time. So this 4 length of, sorry, it takes a time for 4 lengths of the trays, right? So to calculate the different values of speeds at different depths, use the formula 4 multiplied by length of the tray. This will give you the total distance divided by the total time he measures. You can use this formula to calculate the speed of the water waves at different depths. Can be used. Then once you have the depths and once you have the speeds, plot a graph of V against square root of D. If it's a straight line passing through the origin, then the relationship is confirmed. It's confirmed to be true in that case. So verify from the marking scheme, it says speed is 4 times the length of tray divided by the time. Plot a suitable graph. Use the gradient to calculate the G. Well, they use this method, but even if we don't use this method and use that passing through the origin technique, that's also going to give you the marks. They didn't give it over here, but that is accepted. But since this is your marking scheme and this is the point that they want to answer, so yeah, you have to go with that marking scheme. Use the gradient. Okay, what will the gradient of this graph represent? Will it represent G or will it represent square root of G?
It will represent square root of G.
Yes. So calculate the gradient and see what the value of the gradient turns out to be. If it is the same as the value of square root of G, then using that method, you can verify it. That yeah, it's correct. Okay. So we got the marks though. We got almost all the marks. Moving on to the next question. A teacher demonstrates Doppler's effect. Okay, not a part of the syllabus anymore, so we can skip it.
Also, can we see the mark scheme for that answer?
Yeah, it's right over here. This one.
Oh, okay.
Should I move on?
Oh, right. Yep.
14. A longitudinal wave consists of a series of compressions and rarefactions. Compressions means the particles are very close to one another, so the displacement in between them is almost zero. Whereas rarefactions means that they are far apart from one another, meaning they are vibrating at maximum displacement. Now, the diagram shows the position of the particles at equilibrium and the position of the particles at time t. Okay, equilibrium means when all of them are at the same distance from each other. And at time t means when some of them are in the compressed state and some of them are in the rarefacted state. Now, label the point C on the diagram a position where the compression at time t occurs. So this is your compression, right? So it's C. Then take a measurement from the diagram to determine the wavelength of the wave. Well, for the wavelength of the wave, you can either take compression to compression or rarefaction to rarefaction. But since there is just one big rarefaction given to you and not another big rarefaction given to you, so it's better to use the compressions, okay? Because this is one compression and this is the other compression. So this is
Yeah.
going to be your wavelength, lambda. From the middle of our first one
Yeah.
to the middle
Right.
of the second one. And now they're asking us to take a measurement from the diagram to determine the wavelength of the wave. Okay, this is not the wavelength of the wave. This is
Scale.
actually the time period of the wave. So if this is a time period of the wave,
Time is
Part B says a longitudinal wave can also be represented as a sine graph of the displacement of the particles against the distance along the line. On the axis below, draw a displacement distance graph that corresponds to the longitudinal wave. Okay, so as I told you that the compression is the region where the displacement is zero, and the rarefaction is the region where the displacement is max. We have to draw a displacement distance graph in which this idea has been shown. So if this we talk about the start, or if we talk about this point, so it has to return back to zero. If we talk about this point, it has to reach its maximum value, and this point is again going to be at zero. Now if we start out from here, this point is at the maximum position, so the graph is going to go like this, and over here it's going to go in the negative direction max. So this is going to be a sinusoidal shaped curve. Somewhat like this, okay, and over here it will be returning back down. Or this is enough, it's just for 2 marks. Let's see what the marking scheme. Okay, they've drawn it. Wait, they've drawn it. Okay, this is zero, and that's the max, and that's also max, and this is zero again. Sine we've drawn with one wavelength in between compressions, one wavelength in between the two compressions. So these are the two compressions. There must be one wavelength. Okay, one wavelength in between them. And by the way, this is not the only shape that's possible. Okay, you can also draw it the other way around, this way. Let me go back. Right, in between two consecutive compressions, you've got one complete wave, right?
Yeah.
At each compression, the displacement is zero. So to make one complete wave, you have to adjust it such that you adjust one complete cycle over here. So now in between these 2 points, the midpoint is right over here. In the rarefaction, that's also gonna turn out to be zero. So if you're adjusting it to make one complete wave, it's gonna be looking like this, okay?
Yeah.
And now you're gonna continue this.
Then we can continue. Okay.
Yeah, you're gonna continue it over here and continue it in this side as well, but now you have to go down.
Downward.
Yes, but be very careful over here, okay? Okay, this is how you're gonna make the complete wave, okay? And make sure that you make it properly according to the markings, the dotted lines that they have given you. See, the wave is returning back to zero after 1, 2, 3, 4 dotted lines ahead. Right, this is the first box, this is the second one. Sorry, this is the third one, and this is the fourth one. So 4 boxes ahead, the wave is returning back to zero. So on the back side as well, the 4 boxes behind, it will be returning back to zero. Okay, so somewhat like this. Then 15. In a demonstration of the photoelectric effect, the electromagnetic radiation is incident on a clean metal surface. Electromagnetic radiation of this much frequency is incident on a metal surface of work function 3.7 electron volts. Explain why photoelectric effect will be released. Your answer should include a calculation. Okay, why will this question or this demonstration that they have done in the question, why will it cause the photoelectric effect to occur? What was the condition of photoelectric effect? Well, the energy of the photons which are coming, they must be greater than the work function energy. Or in other words, I can say that the frequency of the incident photons should be greater than the threshold frequency. If either of the two conditions are fulfilled, then the photoelectric effect will occur. Correct?
Mm-hmm.
So okay, so what we need to do over here is just find out the energy of the incoming photon and compare it with the work function energy. If it's greater than the work function energy, then yes, a work function photoelectric effect will occur. So why the photoelectrons will be released means why the photoelectric effect will be occurring. Okay, so electromagnetic radiation, the frequency is given to you. We can convert it into energy. So energy is equal to HF. The value for H is 6.63 raised to the power of minus 34 multiplied by the frequency, which is 1.8 raised to the power of 15. This will give you the energy in joules, right? once you get the energy in joules, but this energy is given to you in electron volts. So either convert this into joules or convert that energy into electron volts. I'll convert the electron
Right.
volts into joules. So if 1 electron volt is 1.6 raised to the power of minus 19 joules, then the 3.7 electron volts are going to be how much? So cross multiply,
Cross
get the value
multiply.
for x. And whatever the work function energy is, it turns out to be in joules. Compare these two. If this energy, this one, is greater than the work function energy, then therefore definitely the photoelectric effect will occur. You have
It's
to explain that.
5.92 into 10 to the power 10 minus 19.
And 5.92 is greater than 3.7 into 10 raised to the power. Wait, is that the answer to this, to the first part or the second part?
Second part.
Oh, wait. Okay, this is the work function energy, and the energy of the incoming photons. Can you calculate that too? Or I'll just look at from the marking scheme. It's 1.2 raised to the power of minus 18. And this is greater than the energy which they have given us. This is minus 19, that's minus 18, that's greater, right? So therefore photoelectric effect will occur because the incoming photon energy is greater than the work function energy. You have to mention this, okay? This statement will have 1 mark. What are they saying? Use of HF, energy of photon, conversion, and comparison. See, the comparison has 1 mark. Clear? Got all the 4 points. Part 2 says the electromagnetic radiation transfers energy to the metal surface at a rate of this much. Calculate the maximum number of photoelectrons that can be released every second. Okay, this is the energy which is transferred per every second. Okay, every second we are transferring 1.8 raised to the power minus 9 joules of energy. So how many electrons will be emitted every second? Okay, this to calculate the number of electrons which we can emit using this much of energy. This is the total energy, right? This is the total energy of the emitted electrons. Is going to equal the number of electrons multiplied by the work function energy. Okay,
What was the formula? E is equals to.
HF. But you don't need to
Wait,
apply
how
that.
is this?
Over here, see, this is the total energy which you are providing, and you are they are asking you to calculate the maximum number of photoelectrons that can be emitted. So the total energy is going to be the number of electrons multiplied by the minimum energy required for them to be released, right?
Right.
The maximum energy that is falling, the maximum number of electrons that it will emit would be the energy that it provides. It should be just enough for the electrons. It should be equal to the work function energy. So if you divide this energy by the work function energy, which you calculated in the previous part, 5.92 raised to the power minus 19. So what's the answer coming to that?
Is that minus 9 or minus 19? We'll go with minus 9.
In the denominator is 19, its numerator is minus
Yeah.
9.
To the power of 9.
What's the answer?
3 into 10 to the power of 9.
Okay, this is the maximum number of electrons that can be emitted. Wait, 1.8 raised to the power minus 9 divided by their value in E part 1. The value in E part 1. Wait, that's not the answer. Wait.
Wait, sir, I need to go to the washroom. I'll be right back.
All right, so basically now the electromagnetic radiation transfers energy to the metal at this rate, and calculate the maximum number of electrons that can be released every second. So now in the previous question, we determined that the energy of one electron which is released is this much. Okay, we calculated it over here. This one, this is the energy of one electron. right? E is equal to hf. We use that formula, and the energy which is required by one electron to be emitted is this much. How many electrons would be emitted if the energy provided is 1.8 raised to the power of minus 9? Okay, so just cross multiply, find out the answer. It's going to be 1.8
Okay.
1.8 raised to the power of minus 9 divided by, it's 1.5 raised to the power of 10, and that is wait, it's 1.5 raised to the power of 9, sorry, it's 1.2 raised to the power minus 18 in the denominator, not 19. This is 18. Okay, it's 18. So yeah, it's 1.5 raised to the power of 9, and that's the answer. When the photoelectrons are released instantaneously, explain how this provides evidence for the particle model of light and not the wave model. Okay, a very frequent question, again repeated, was asked in the previous paper as well. So why are the photoelectrons are released instantaneously? Why is this particle nature and why is this not a wave nature? Because each electron emitted absorbs one photon. Each electron absorbs a photon and is emitted instantaneously. If the photon energy is more than the work function, right? In case of wave model, regardless of the frequency or the energy, regardless of the photon energy, photoelectric emission will still eventually occur. That's the difference in between the wave model and the particle model. Take a picture of this answer. Microwave ovens are used to cook food. Microwaves are emitted inside the oven and reflected in the sides, forming standard waves. Okay, you've got the microwaves that reflected and standing waves are generated. And what are standing waves? Waves which are formed as a result of overlap between two waves which are traveling in the opposite direction, and constructive and destructive interference occurs, due to which you get nodes and you get antinodes. Antinodes are positions where the displacement is max, and nodes are the positions where the displacement is zero. Explain how hot and cold spots are formed within the food. Well, why will there be hot spots and why will there be cold spots? Hot spots would be representing the regions where the amplitude is going to be max. Amplitude is max. And cold spots be representing those positions where the amplitude or the energy is going to be zero, or the displacement is going to be zero. Okay, so amplitude is max at the antinodes and is zero at the nodes. Antinodes are formed as a result of constructive interference. Nodes are formed as a result of destructive interference. So that's why you get the cold and the hot spots. Okay. For 3 mark, these are actually the 3 points that they want you to answer. What does the marking scheme have to say? Okay, cold spots formed at the nodes and the hot spots are formed at the antinodes. Okay, we just mentioned that, got that mark. Nodes formed when they meet an antiphase or when there is zero amplitude. All right, we got that mark as well. Now, antinodes are formed as a result of maximum amplitude. We got this mark as well. Okay, we got all the 3 marks. Is this clear?
Yeah.
Okay, then the part B says, or part 2 says, a distance between two adjacent spots in the food is given 1.4 centimeters. Calculate the frequency of the microwaves. Okay, two adjacent hot spots. Hot spots mean two antinodes, right? Two adjacent antinodes, the distance in between two adjacent antinodes. All right, what's the distance in between two adjacent antinodes in a stationary wave? For instance, if this is your stationary wave, it goes forward, just returning backward. All right, hot spots mean two antinodes in between these 2 points. What is this distance representing? Is it representing lambda by 2, right? Because the distance in between the antinode and the node is lambda by 4. So 2 times lambda by 4 is lambda by 2, right? So
Right.
lambda by 2 is actually 1.4 centimeters. That means lambda is 2.8 centimeters. If you got the lambda, can you calculate the frequency using the formula V is equals to F lambda? V is going to be the same as the speed of light because these are microwaves, electromagnetic waves traveling at the same speed as light. And when you divide that by the wavelength, which is 2.8, and centi needs to be converted, do not forget to convert that, you'll get your frequency. Okay, and write it down over here. Moving on, suggesting how the effect of cold and hot spots is reduced by placing the food on the rotating turntable. Okay, how the effect of hot and cold spots is reduced by, and this is a just type question. So how can, okay, they told us it's a rotating turntable. What would rotation do? Will it continuously replace their position? Will it continuously change the position of hot and cold spots? Right, rotation would change the position of hot and spot colds. So their effect is going to be reduced. So the position of hot and cold spots is reduced continuously. Position is changed and so effect is reduced. It's verified. They did the same thing. V is equals to F lambda. Lambda is this much and so okay. The positions are constantly changing. Yeah, rotating means the same thing. So yeah, they actually gave the answer in the question. They told us they are rotating, and rotating means that yeah, the position will be changing. Okay, we got that mark. Is this clear? Any doubt?
Yes.
Okay, no doubt. Then part B.
How are the hot and cold spots produced?
Nodes and antinodes, we gave that answer in this part. Remember,
Okay.
antinodes are the hot spots because these are the spots
Oh, okay. Right.
moving with displacement such as max. Okay. Now, part B says the interference of microwaves can be investigated in the laboratory using the microwave transmitter and the receiver. This is a transmitter, this is a receiver. Is this similar to the Young's double slit experiment, if you remember? Right? You've got the double slits, you've got the wave being produced from here. This wave will be diffracted at this slit and diffracted at this slit, producing two coherent waves over here. And then this receiver is moved. Okay. So as a result, what would happen? Constructive and destructive interference would happen, and you'll get maxima and minima across this length. Now, alternating points of maxima and minima are observed. Explain why O is a point of maximum reading. Why is this O a point of maximum reading? You have to just explain why a maxima is formed. So start out from the basics. Diffraction occurs, two coherent waves are generated. The waves, they travel to the point O. As soon as they reach the point O, constructive interference occur, due to which a maxima is produced. But why will a constructive interference occur when the path difference in between them is, in between the two waves from these slits is going to be 0? Why is the path difference 0? Because if you look at these two slits, if you measure the distance from this slit to the O and this slit to O, oh, sorry. If this, the length of this path is L, the length of this path is also going to be L. So the two waves will travel equal distance as they reach O. So the path difference, what is going to be the path difference over here? The path difference will become 0, the difference in between the two paths. And whenever the path difference is either 0 or lambda or 2 lambda or 3 lambda and so on, you get constructive interference. Okay, that's why you get no antinodes, antinodes. Got it? I'll write down the answer. The two coherent waves which are produced at the slits, the two coherent waves produced at the slits due to diffraction shall travel the same distance as they reach O, or will travel equal distances as they reach O. So path difference is going to be 0. If path difference is 0, then what happens? Therefore, constructive interference would have occur. and a maximum reading is obtained. Okay, and not actually an antinode. Okay, not antinode, because antinode is used for stationary waves, not for these waves. Explain why the maxima and minima readings are observed alternately as a receiver is moved along the line AB, because as we go up and down, both constructive and destructive interference would occur. Okay, as this receiver is moved along this line, destructive and constructive, destructive and constructive, destructive and constructive interference would occur. That is because at different points, the path difference in between them would keep on changing. Path difference keeps changing, and there are points in which and so the wave at points is in phase would result in maximum readings, and the points where the wave is out of phase results in minimum reading. Maxima has a path difference of n lambda and n plus half lambda. Okay, they gave it in terms of path difference. Path difference keeps on changing. For maxima, the path difference in phase, the path difference must be n lambda. If you remember, it's gonna be, or you could say that it should be in this range: 0 lambda, lambda, 2 lambda, 3 lambda, and so on. For minima, it's gonna be lambda by 2, or 3 lambda by 2, or 5 lambda by 2, and so on. Okay, so this happens as a result they're out of phase and stuff. These points will gain you all the marks. Is this clear?
Yeah.
17. Diagram shows some of the energy levels of the hydrogen atom. Okay, these are the energy levels in between which the electrons can excite and de-excite. Explain what is meant by the ground state of an atom. Ground state means the lowest possible energy of an atom, the lowest energy state, or
That
the
is zero.
most stable state of the atom, lowest energy state of atom. Verified from the marking scheme side by side. Atom having the lowest possible energy. Okay, then part B says under certain conditions electromagnetic radiations of this much wavelength are emitted. Determine the transition which would result in the emission of electromagnetic radiation of this wavelength. Okay, this is the wavelength which you got. Which transition would give us a wavelength being emitted? Okay, for emission to occur, electrons has to de-excite. Okay, to emit waves, it has to de-excite. Now, the different transitions that are possible are from 0 to minus 3.39, or from 0 to minus 1.51, or from 0 till here, or from here till here, or from here till here, or from here till here. Okay, many are possible. Now we need to find out the transition which resulted in that wavelength. For that, we'll need to find out the energy of that wavelength and then convert it into electron volts, and then compare it with the energy gaps in between these different energy levels. The one which matches is the answer. Okay, so first find out the energy of this wavelength. So energy can be calculated using the same formula HF, right? F means C upon lambda, right? So velocity upon wavelength. So HC upon lambda. Use it, calculate the value, 6.63 raised to the power minus 34 into the 3 raised to the power of 8 divided by 122 is nano raised to the power minus 9. This will give you an energy in joules. Now, once you have the energy in joules, you know that 1 electron volt is 1.6 raised to the power minus 19 joules. Convert that energy in joules to electron volts. Once you have that energy in electron volts, compare it with the energy gaps over here and see this energy that you have gotten. This is actually that difference in between those two gaps. Okay, once you get this difference, see which of these will be that transition. If you look at the marking scheme for the answers, so it's 10.2 electron volts that we got. 10.2 electron volts is the answer, final answer. So look at these gaps and see which of these have a difference of 10.2, and it's these two, I think. 13.6 minus 3.39. What's the answer? 10.21. Yep. So this is the transition. And remember, it's going to be from minus 3.39 to minus 13.6. Okay. Not the other way around, not this one, because this will not emit any wavelength. This will rather absorb wavelength. It's going to be minus 3.39 to minus 13.2. Clear? 13.6, sorry. Is this clear? And
can you repeat the steps again?
okay, so you need to find out the energy of the wavelength. Use the same formula HC upon lambda. You got it in joules. Convert that
Okay.
into electron volts. It turned out to be 10.2.
Okay.
Now, this electron volts energy, see which of these energy levels have a difference of 10.2. Okay, and it's these two.
Okay.
So as the electron moves from minus 3.39 to minus 13.6, it's going to emit a wavelength of 122 nanometers. Clear? Now, part 2 says identify the part of the electromagnetic spectrum to which the radiation of the wavelength belongs. Well, this is something you need to learn. 122 nanometers, that's for ultraviolet. Okay, this is a theory part. The wavelengths
Wait,
needs to
how
be
would
learned.
we know?
You have to learn it. This is
Oh no.
theoretical, yeah. Ultraviolet. Then 18, a car has 4 identical side lights. They are connected to the battery of the car as shown over here. Okay, this is your battery, this is your switch, and this is internal resistance. These are the side lights. Okay, they are all in parallel to the battery, but if you look at it, the battery has a resistance, internal resistance. Derive an expression for the electromotive force in terms of I, resistance of the battery, and the resistance of each bulb. All right, the resistance of each bulb is R. Okay. What's their total resistance? Well, you've got the 4 bulbs in there. The total resistance is going to be R upon 4 because all of them are in parallel. Correct?
Right.
Okay. Now, if you have the total resistance and you have the current and you have the EMF and you have the internal resistance, you can derive an expression, okay, using Kirchhoff's second law. But you have to show these steps. Okay, the total resistance of the 4 bulbs is R upon 4. And then once you have this, then you can use Kirchhoff's law. The EMF of the battery is equal to I multiplied by R plus I multiplied by R upon 4. That's your answer. Okay, I into R plus I multiplied by R upon 4. Clear? Is this clear?
Yeah.
All right, so let's verify it. Yeah, that's the answer. Then next one says, part C actually, no, part B. The side bulbs are on. The current through each bulb is 0.43 amperes. Calculate the power dissipated in R when R is this much. Okay, current is given to you through each bulb, meaning 0.43 is the current in this branch, in this branch, in this branch, and in this branch. So what would be the total current flowing through R? It's going to be the sum of all of these, right? So it's going to be 0.43 into 4, which is how much? It's 1.72 amperes. Now you've got the current, and they've also given you the value for the resistance of R, which is 0.025. 0.025. Now you have the resistance, you have the current. Can you calculate the power? Which formula should I use if I have these two values? I squared R, right? It's going to be 1.72 squared multiplied by 0.025. And the answer to this is going to be your final answer. Is this clear? Okay. You have a starter motor which is briefly connected in parallel across the battery. The starter motor draws a current of 120 amperes from the battery. Explain why the side lights will dim as the engine is started. Okay, engine is started means to start it, the starter motor will be briefly connected and it will draw out a current of 120 amperes from it. So if you've got the battery over here and let's assume this is your starter motor connected over here, some load. Okay, and the only current flowing to that starter motor is 120 amperes. So the total current now, the total current flowing through this resistor, will it rise? The total current through the resistor will rise, correct? So what's the terminal
Okay.
potential difference formula? The
E
terminal
is equals
potential
to V
difference,
minus V is equals to E minus IR.
yes, is E minus IR. If I increase the value for the current, what will happen to the terminal potential difference? Will it fall?
Yeah. No, no, no.
Yes, yes, it will fall because this is negative, right? Right?
Right.
Okay, so if it is falling, then that means that the potential difference across these two terminals, it will decrease. And this potential difference is actually the potential difference across each of these bulbs. The potential difference across each of these bulbs will also fall, due to which they'll become dimmer. Okay? So more volts are lost in the internal resistance. Okay? Explain why the side lights were dim as the engine is started and it is put parallel to the battery. Okay, starter motor, it draws a current of 120 amperes from the battery. So as the starter motor is connected, the current is 120 amperes, which is more than the previous current, which is much more than the initial current. Then give the formula for the terminal potential difference. Terminal potential difference are actually those volts which are available to the circuit, okay, after the volts which are lost in the internal resistance. So the EMF minus IR. Now, as the current increases, the lost volts in the internal resistance also increase. The lost volts in the internal resistance will rise, and therefore the terminal potential difference will fall. Terminal PD will fall. Since the light bulbs are connected in parallel, the potential difference across each one of them will fall. Okay, therefore they'll become dimmer. Let's look at the marking scheme now. Okay, there is a current, increase in current through R. There will be a large potential difference of more lost volts. Terminal PD will fall, reducing the power of the side bulbs. Got the marks. We didn't mention this. We should mention that point as well. So add this one. This will reduce the current. Or we did mention the PD. So yeah, we did actually get that mark as well. PD is actually referring to the power. Get it? You get this answer?
Wait, I'm reading the answer.
Most probably. Okay, student plots a graph of current against potential difference for an LED, a light emitting diode. Okay. Now this is your a typical diode graph. Now state the measurements the student should make to plot the graph. Your answer should include a suitable circuit diagram as well. Okay. To plot this graph, we need the current, we need the voltage across the diode actually. Okay, so a student plots a graph of potential difference across an LED. Okay, so for the circuit diagram, if you look at the circuit diagram first, you need a battery which is connected across a diode, a light emitting diode. And in addition to that, you also need some other resistor to control the flow of current. Okay, to control the flow of current, the resistor should be a variable one. Okay, so you have a variable resistor. Now to calculate the potential difference, oops, sorry. Calculate the potential difference, this V, you need to put in a voltmeter as well in the circuit to measure it actually. And to measure the ammeter, to measure the current actually in the circuit, you need to put in an ammeter. This is how the circuit diagram should look like. Now, what should the measurements should the student take to plot this graph? The student should measure the voltmeter readings. First of all, he should vary the current using the variable resistor. Then, at each corresponding resistance, read off the value from the ammeter. Read each corresponding current value. For that and corresponding voltage, All right. Now, if you look at the graph is in both in the positive direction as well as in the negative direction. So for the negative direction means that the polarity of the diode has been reversed, right? So for the negative direction graph, just reverse the polarity of the diode, right? You don't need to reverse it on the diagram, but like you just mentioned it. Then reverse the polarity of the diode, reverse polarity of the diode. And the diode will have maximum resistance because it would be in the reverse bias direction. The diode will have maximum resistance in reverse biased order. Okay, let's see. Measure the current and the corresponding potential difference for a range of values. Okay, range of values is important because you are doing an experiment. So, and of course, you need to draw a graph. You'll need a range of values. Vary the current and for a corresponding voltage for a range of values. Okay. Then reverse the supply of the diode. Okay, we did that, meaning the polarity. Which ammeter correctly connected the means of varying it. Also, yeah, we did that. We added the variable resistor. Okay, we got all the 4 points. Is this clear?
Yep.
Okay. V part 1, determine the resistance of the LED when the voltage is plus 2 volts. Okay. For the resistance R is equals to V upon I. The voltage is given to you is 2. What's the current? The corresponding current value at that point. The voltage is 2. It's right over here. Voltage is 2. The corresponding current value is going to be 225. And then it's 225 milliamperes. This is the current. The voltmeter reading is 2 volts. So R is V upon I. So 2 upon 225 raised to the power minus 3. Then this will give you your resistance. Okay. Same thing. Clear?
Yep.
Then part 2 says state the resistance of the LED when voltage is minus 2. When the voltage is negative, negative means it will have infinite resistance. Okay, meaning no current is flowing. See, no current is flowing over here. So that means the resistance is very, very large. Infinite, very large. C. The student is told that the LED will be damaged if the current is too large. To avoid the damage to the LED is connected in a circuit so that it is in series with the resistance or resistance R to limit the size of the current. Okay, so we've got this. Actually, it's quite similar to our circuit diagram. And by the way, if you look at this symbol of LED, we didn't put in that symbol over here. So do put in that symbol as well. A circle with 2 arrows coming out representing the light. Now, with reference to the current potential difference characteristic, state why without the resistor, the current through the LED could become way too large. Okay, with reference to the current potential difference characteristics. Okay, if the volt, if there is no resistance, then that means all the potential difference would be provided to the diode, right? And if you remember the formula Ohm's law, V is equals to IR, the diode is connected in the forward bias direction, right? It's connected in the forward bias direction. That means
Yeah.
the resistance is going to be very low for the diode, right? And all the voltage is provided to the diode in absence of the resistor. In absence of this resistor, all the voltage would be provided to the diode. All the 6 volts would be provided to the diode. And since the resistance is low and the voltage is high, then automatically the current flowing through it is going to become very large because of the Ohm's law condition. Okay, so you have to mention this down that resistance of the diode is very low due to forward biased configuration. And then all the voltage is provided to the diode. So current is going to be very large. Resistance is too low. That's the answer. Okay, I got it. Then part 2 says intensity of light emitted by the LED depends on the magnitude of current through the LED. 95% of the electrons flowing through the LED cause a photon to be emitted. Okay, the rate at which the photons are emitted is this much. Use the graph to determine the value for the resistance that will produce the rate of emission. This rate of emission. All right. It's 1.6 raised to the power of 18 photons being produced in 1 second. Okay. And the energy of these photon. Okay. So we need to look at the graph now to determine a value for R that will produce this rate of emission over here. They're saying that one photon is emitted by 95% of the electrons flowing through the LED. Okay, so the current which is flowing, so tell us which the rate at which the photons are emitted by the LED is this much. So which resistance will have this number of photons which will be emitted? This number of photons means this many electrons are flowing. No, actually not this many electrons. The number of electrons which are flowing, this is actually the 95% of it, not 100% of it. So what's the 95% of this? 95% of this number is going to be the number of electrons which are flowing, right? The number of electrons which are flowing in the circuit, because only 95% are emitting the photons and not all of them, not the 100% are emitted. So 0.95 when you multiply that by, meaning, yeah, 0.95 when you multiply it by 1.6 raised to the power of 18, this will give you 1.52 raised to the power of 18 as well. These are the number of electrons which are flowing through the circuit. Clear? Now you have the number of electrons flowing through the circuit. Can you calculate the current flowing through the circuit? It's also going to be the same, because current is the rate of flow of charge. These are the electrons flowing in 1 second. So that's the current, 1.52 raised to the power of 18 electrons. Actually, these are the number of electrons. These are not the charge of the electrons, right? So current is a flow of charge, rate of flow of charge. So what's going to be the charge of all of these electrons is going to be just multiply them by the charge of a single electron. Multiply by the number of electrons by the charge of electrons. So it's going to be 1.6 raised to the power of minus 19 multiplied by this answer. And this 1.52 raised to the power of 18 multiplied by 1.6 raised to the power minus 19. This turns out to be 0.2432 amperes. Now you have the current flowing through the circuit. 0.2432 amperes. Now to compare this with the graph that's given to you. It's given to you in milliamperes. So can we convert this into milliamperes? Definitely we can. Current in milliamperes just multiplied by 1000. So it's going to be 243 amperes, 0.2 amperes. Now look at the graph and see what's the corresponding voltage at 243. You zoom in a bit, 225, 230, 240. It's going to be approximately somewhere here. So it's going to fall down somewhere over here. Going to fall down from there. Okay. This is going to be 2.2, sorry, 2.1 volts. 2.1 volts is the voltage when the current is 243 amperes. So now you've got the voltage as well. Now you have the voltage and you have the current. Can you calculate the resistance? R is V upon I. It's going to be 8.63 raised to the power minus 3 ohms. Quite a low resistance. Let's see. Their answer is different. Q is equals to IT. We did use this. We did use of 95% graph. Calculate I and LED. Then V is equals to IR. VR is V minus VLED. I think there's some problem in the calculation. Just a sec, let me check. It's 1.52 raised to the power of 18 multiplied by 1.6 raised to the power minus 19. 1243. Okay, now you've got the current. In this question, they were actually asking you to find out the value for R. What is R? R is not the resistance of the LED. It is rather the resistance of this resistor. Okay. So now what you need to do is follow these steps. First of all, they gave you the number of electrons, photons which are emitted, right, per second. If this many electrons are emitted photons are emitted per second, how many electrons will be passing? So for the number of electrons which are flowing over here, these are just the 95% of them, right? The number of electrons. Let's assume the number of electrons are X. Okay, 95% of these X are actually equal to 1.6 raised to the power of 18. Now find out the value for X. Value for X is gonna be, rearrange it, it's gonna be 1.6 raised to the power of 18 multiplied by 100 divided by 95. Now you've got the number of electrons flowing through this circuit in 1 second. Can you calculate a value for this, please? 1.6 raised to the power of 18 times 100 divided by 95. So it's 1.68 times 18. Clear? Now these are the number of electrons which are flowing through the circuit. If you've got the number of electrons, you can get the current as well, because current is the charge upon time. Time is 1 second, but what's the total charge if these are the electrons? Multiply them by the charge of one electron. 1.6 raised to the power of minus 19. So it's gonna be
Wait, how do we know equal security for
0.27 amperes. How do we know what? How do we know? How
like we have to use I is equal security formula?
to get the current, because once we have the current, only then will we have the voltage from this
Okay.
graph. Okay. Now, once you have the current, it's 0.27 amperes. Now, this 0.27 amperes current, this can be used to get the voltage from the graph across the diode. Okay, the voltage across the diode. 0.27 on the graph is gonna be 0.27 amperes actually means 270 milliamperes. The 270 in this graph, this is 250, 260, 270. It's gonna go all the way on the graph. Read it off. This 270 is 2 boxes ahead. It's 2.2 volts, right? On the x-axis is 2.2 volts. So now once you have the voltage, 2.2 volts, this is the voltage across the diode. In this circuit, this is the voltage across the diode, 2.2 volts. What's the voltage across the resistor? It's gonna be 6 minus 2.2, right? Is this clear? It's gonna be 6 minus 2.2, the voltage across the resistor. Hello? It's gonna be 3.8 volts. Okay. Now, once you have the voltage across the resistor and you know that the current flowing through the circuit is 0.27 amperes, then you can use them to get the value for R. R is V upon I is 3.8 divided by 2.7, and this turns out to be how much? 14 ohms, 14.1 ohms. Finally, we got our value for resistor R. Is this clear? Now, if you remember from theory, the work done per unit charge, work done per unit charge is actually the definition of potential difference. right? Which is actually the definition of voltage. The voltage across this resistor is 4.2 volts. They're telling us that is energy, the energy of the emitted photon is 77% of this work done. Okay, so now what is the work done? If this voltage is 4.2 and the work done is W and the charge of one electron is 1.6 raised to the power minus 19, we can get the work done on that electron, right? Now, and actually wait, this is the work which is done. Uh, the energy of the emitted photon is the work done on the electron as it moves through this potential difference, as it moves through 1.8 volts. As it moves through 1.8 volts, the energy in that case, not through 4.2, as it moves through 1.8 volts, as it moves through this potential difference, right? This one, 1.8 volts. You have to consider that in your calculations, not the 4.2. The work done, which turns out to be, is going to be 1.8 into 1.6 raised to the power minus 19. What's the answer to this? Can you calculate this value, please? 2.88 raised to the power minus 19 joules. You have the work done. What's going to be the energy? Is going to be 77% of this work done. 2.2 raised to the power minus 19 joules. Yep, that's the answer. Get it?